Hello students. So let's continue our NCERT chapter 7, that is alcohol, phenols and ethers. And today is the theory part 11. So this is the disclaimer. Now what is the objective of today's lecture? So after attending this lecture, you will be able to understand the topics which we are going to discuss today. So today we will discuss the reactions for the preparation of ethers from alcohols and alkyl halides and sodium alkoxides aryl oxides. And we will correlate the physical properties of ethers with their structures. So for your reference, I have mapped the NCERT sections that I am going to cover today. So today I'll be covering section 7.6, that is ethers, and the subsection 7.6.1, that is preparation of ethers. 7.6.2, physical properties, and then we'll solve one example, that is 7.6. And we will also solve our NCERT exercise question, which is 7.25. Okay, so let's begin with the lectures. So we discussed about the chemical reactions related to phenols. We discussed it about alcohols. Today we will discuss about ethers. So before going to the reactions of ethers, first let me give you a brief introduction about the ethers, that how do ethers look like and how do we name ethers according to the common name and according to the IUPAC nomenclature. So how ether is formed? When in an hydrocarbon, the hydrogen atom is replaced by an alkoxy or aryloxy group. Now see the word alkoxy. So what comes to your mind by seeing this word? That something is connected with oxygen. Some R group is connected with oxygen. So that is an alkoxy or an aryloxy group. So the hydrogen atom of the hydrocarbon is replaced by an alkoxy or aryloxy group. So if we do the classification of ethers, then it can be classified into two: symmetrical ethers and unsymmetrical ethers. So first let us see what are symmetrical ethers. The symmetrical ethers are also called as simple ethers. So in symmetrical ethers, the two groups that is attached with the oxygen, they are same. Okay. If you look at this example, you see that there is oxygen in between and the two groups on your right as well as on your left side, they are same. Here it is also methyl group and here also it is methyl group. So this is simple or symmetrical ethers. So how do we name them according to IUPAC nomenclature? It is named as alkoxy-alkane. Okay. So in alkane, we take the longest carbon chain and then the O with the R group is taken as alkoxy part. So if you see here on both right and left side, there are same number of carbon atom. Here also there is one carbon atom and here also there is one carbon atom. So both carbon atoms are same. So we can take either one of them as alkane or methoxy one. Okay. So we will write this group, which O, and this CH3 group. It is written as methoxy. Okay. And this alkane group is methane. So it is methoxymethane. And it is symmetrical in nature. Symmetrical, if you cut this molecule from between, then both the sides will be same. It is a symmetrical ether. Now if I talk about mixed or unsymmetrical ethers, then in this, the groups that are present or that is attached to the oxygen on your left and right sides, they are different. That means both the groups are different. Look at this example. At right side, you will see a methyl group is there. And at this side, you will see a benzene ring is there. So both the groups are different. So this is a mixed or an unsymmetrical ether. Now, if I name this according to IUPAC nomenclature, then I told you the one which has the longest carbon chain is your alkane. So if you see here benzene, it has 6 carbon atoms. So this benzene part will be your alkane part. And then this O and R group will be your alkoxy part. So here it is 1 carbon atom only. So the root word will be meth. So it will be methoxybenzene. Okay. So this is how we do the nomenclature of the ethers. So there are two types, simple and mixed. So whenever your hydrogen of an hydrocarbon atom is replaced by an alkoxy or an aryloxy group, then an ether is formed. So this was the introduction about ethers. Now let us move to the preparation of ethers. So ethers, it can be prepared from the following reactions. Ethers can be prepared from alcohols. You will see that how we treat alcohols under certain conditions, which gives us ethers. And next is from alkyl halide. And this process is called as Williamson synthesis. So from Williamson synthesis, we can prepare your ether from your alkyl halides. Halides means like fluorine, chlorine, bromine or iodine. That is the X group. Now one by one we will see from both these reactions that how are we preparing our ethers. So first is dehydration of alcohol. So if you see the word dehydration, first what thing comes to your mind? So dehydration, something in which there is removal of water. In summers it is asked to drink more and more water. Okay, so that you don't become dehydrated. So in chemistry, this dehydration means that water is being removed. Okay, so your alcohols, they undergo the dehydration in the presence of a protic acid. Now, if this is dehydration, that means water removal. So you need an agent that can remove your water from alcohol. So what will that agent be called? It will be called as dehydrating agent. Okay, and in this reaction, that dehydrating agent is your protic acids, that is H2SO4 and H3PO4. Protic acids which easily gives up a proton, that is H+. Okay, so what happens in this dehydration? You have two alcohol molecules, ROH and ROH. And when you treat it with a protic acid, water is removed. How? From one alcohol, hydrogen is removed, and from another alcohol, your hydroxyl group is removed. That is OH group. So what goes out? H2O. And what is left behind? ROR. So that is an ether. So this is how it takes place. So one side there is alkyl group and other side there is an alkoxy group. Now what happens in this dehydration of alcohols? Whether your ether will be formed or your alkene will be formed depends upon your reaction conditions. I mean to say, whenever if you are taking an alcohol in presence of a protic acid, it is not always necessary that an ether will be formed. Whether ether will be formed or something else will be formed is depending upon your reaction conditions. In chemistry, your reaction condition plays a very important role. Okay, whatever the conditions are there around the reaction, it proceeds according to that manner. So here also you will see that not always ether is being formed when alcohol is treated in the presence of a protic acid. That is in dehydration of alcohols. So what will happen if the temperature will be high? If the temperature is 443 Kelvin, then instead of your ether, your alkene will be formed. And when your alkene will be formed, then it occurs by an elimination reaction. Okay, it do not go by a substitution reaction. This alkene is formed by an elimination reaction. So if you look at this reaction, this is an alcohol which is called your ethanol. Okay, it is treated with a protic acid, that is H2SO4, and look here, the temperature is high. It is 443 Kelvin. So in this case, your alkene is formed, ethene is formed. You can see carbon-carbon double bond is there. Okay, and water is being released. Now this reaction occurs by elimination and not substitution. So what happens first, if this is your alcohol, first we kindly protonated this alcohol. We kind of protonate this alcohol. So that when we protonate this alcohol, it is OH2 plus. So when it is OH2 plus, this oxygen will now have a positive charge. So oxygen will leave from here, OH2 group will leave from here, and a carbocation will generate. Okay, and then your carbocation will generate on this carbon. So what will happen? One hydrogen from one carbon and plus from other carbon leaves, and you get an alkene. That is, this alkene is then formed. Okay, this happens when your temperature is 443 Kelvin. That is, when your OH2 group leaves from here, a carbocation is generated, then H plus leaves, and you get an alkene over here. Here it is ethene. Now if the temperature is low, if the temperature is 413 Kelvin, then you will see with your alcohol, ether is being formed. And this reaction, it occurs by a substitution reaction. That is SN2, bimolecular substitution reaction. So here substitution takes place. And in this case, you will always form a symmetrical ether. So always a symmetrical ether will be formed in this case. Now look at the reaction. Here we are taking 2 moles of your ethanol. That means 2 molecules of ethanol we are taking. When you are treating it in presence of a protic acid, see here you are getting diethyl ether and water is being removed. So if you want to understand in simple terms that how you go from the reactant to product, that is, we remove water. That is hydrogen from one alcohol and hydroxyl group from other alcohol. So if water gets removed and you are left with your ROR group. So this is a symmetrical ether. On your right side, it is also a ethyl group is there. Here also it is a ethyl group. So if you see here diethyl ether, this diethyl ether is a common name, not an IUPAC name. Okay, so when you write a common name, you follow the alphabetical order. Whichever letter comes first, you write that thing first. But here, since on both sides there is ethyl, so it doesn't matter. So since there are 2 ethyl, so you will write diethyl ether. So common names is written in the form alkyl ether. So here there are 2 ethyl groups, so you will write diethyl ether. Okay, so this happens in dehydration of alcohols. You need to remember this thing, that not always your ether is formed if you are taking an alcohol in presence of a protic acid. If the temperature is high at 443 Kelvin, then when your ethanol reacts with your protic acid, you get an alkene. Here it is ethene. And when temperature is less, that is 413 Kelvin, then your alcohol is formed in the presence of protic acid, and it occurs by the substitution reaction. Now we will see that how from the alcohol we are getting the ether. We will see the mechanism of this. Okay. So if you saw, then your dehydration of your ethanol, it produces ethoxyethane, which is commonly called as diethyl ether. So this is common name is diethyl ether and IUPAC name is ethoxyethane. IUPAC name is written in the format alkoxyalkane. So it is ethoxyethane and water is released. See, the temperature is less, that is 413 Kelvin. So in this case, your ether will be formed. Now what happens in this reaction? As I told, that this reaction occurs by SN2 mechanism. Okay. And in this reaction, there is a nucleophilic attack. So it is bimolecular substitution reaction. So in step 1, it is protonation of ethanol. Because if we want a nucleophile to attack, then there should be a positive charge. Because nucleophile loves positive charge. So for nucleophile to attack, we have to protonate our alcohol, which is ethanol over here. So see, this is an ethanol, CH3CH2OH. We will protonate this ethanol. From where this H plus is coming? Of course, from a protic acid, that is H2SO4. It readily gives a proton. Okay, so now this oxygen has the electron density, and this hydrogen has a positive charge. This is electron deficient. So this is here a electrophile, and this oxygen has electron density to donate. So it will give its electrons to this hydrogen, and you will see from this ethanol, a protonated ethanol is formed. On oxygen, you will see there is a positive charge. So this is a protonated ethanol. Now what will happen? A nucleophile attack will happen. So from where will we get nucleophile in this reaction? Can you guess? So students, see here we have taken 2 moles of ethanol. That means we are having 2 molecules of ethanol. So if one has reacted here, then one must be left. So that will act as your nucleophile over here. Okay. The second step is that your protonated ethanol, it is attacked by the second ethanol molecule to form a protonated ether. Look here, this is your protonated ethanol which we got from step 1, that is CH3CH2OH2. On oxygen, you have a positive charge. Now this oxygen never likes the positive charge because it is an electronegative atom. So this never likes positive charge. So this always wants to leave if it has a positive charge. Now see, we have another ethanol molecule. Now on this ethanol, this oxygen has electron density to donate. So what will happen? This will act as your nucleophile. So here your ethanol is a nucleophile over here. So what will happen? Your oxygen will attack on this carbon and this OH2 will leave. Okay. So see, this oxygen has attached on this carbon and this OH2 group has leave. So now we have formed a protonated ether. See here, CH3CH2O, and this hydrogen is this, and your CH2CH3 group has been attached and water has left, and this oxygen now has a positive charge. Okay. So see here, ether has been formed. One side you have alkoxy group, other side you have an alkane group. Okay, both side there is CH3CH2 and this side also there is CH3CH2. So first step is the protonation of ethanol, and then there will be nucleophilic attack in which your second molecule of ethanol, it will attack on your protonated ethanol to form a protonated ether. So now what will happen in next step? The oxygen has a positive charge. So it will try to remove that positive charge. So after deprotonation of protonated ether, diethyl ether or ethoxyethane is formed. That is, there will be deprotonation of protonated ether. That this hydrogen will be removed from here. So this H plus proton is removed and you get your neutral molecule which is ethoxyethane. See again, on both left and right side, you have 2 carbon atoms. Okay, so it is ethane only on both the sides. So you can take any one of them as alkyl group, alkane group, or alkoxy group. So if this is alkoxy group, this is ethoxyethane. And this H plus is left from this group. Okay, so this proceeds in 3 steps, and this proceeds by SN2 mechanism. That is bimolecular substitution reaction. So when the temperature is 413 Kelvin, from your alcohols, your ether is formed. And when the temperature is 443 Kelvin, then from your alcohol, alkene is formed by elimination reaction. So this was from the dehydration reaction. Okay, I hope this is clear now. Now we will see Williamson synthesis. That what happens in Williamson synthesis. So in Williamson synthesis, you will get an unsymmetrical ether. Okay. Now if you look here, then alkyl halides, they are reacted with sodium alkoxide to form an ether. So you will take an alkyl halide and then it will be reacted with sodium alkoxide. Sodium alkoxide, that is RO minus Na plus to form an ether. Now see here, you have an alkyl halide, that is Rx, and you have a sodium alkoxide, okay, that is R dash O minus Na plus. Now what will happen in this reaction if I tell you in brief over here, then this oxygen has an electron density, okay. So if this oxygen has an electron density, it will attack with its electrons on this R group. And when it will attack with its electrons on this R group, then this halide will leave from here. So what will be left? ROR dash. And your NaX, that is sodium halide, has left from here. Okay. So this is how from alkyl halide you will form an ether by reacting it with sodium alkoxide. Now here you can produce symmetrical and unsymmetrical ethers. If your R and R dash group is same, there will be a symmetrical ethers, and if group is different, then there will be unsymmetrical ethers. Now this reaction proceeds through an SN2 pathway. Okay, that is that your nucleophile, it will attack from backside. So it is going by SN2 pathway, that is bimolecular substitution reaction. Now look at this example. Now when we talk about Williamson synthesis, then in Williamson synthesis there is one catch. Okay, that your alkoxide group over here, if you see, is tertiary alkoxide group. This alkoxide, this is tertiary butoxide. So this is a 3-degree alkoxide. And if you see alkyl halide, it is a primary alkyl halide. So in Williamson synthesis, it is preferred that you take a primary alkyl halide and tertiary this butoxide. So if you will take primary alkyl halide, in that case only you will form an ether. If in case you reverse, that means your alkyl halide is tertiary alkyl halide, then in that case, if it is tertiary or secondary alkyl halide, then what will happen? In that case, ether will not be formed. Alkene will be formed. So this is the catch in Williamson synthesis. Okay. So if you see here that this is an 3-degree alkoxide. Why? See, this carbon is further connected by 3 carbon. 1, 2, 3. So this is a 3-degree carbon. So this is 3-degree alkoxide. How will you name it? 2-methyl propane 2-olate. Okay. And this is your primary alkyl halide. Okay. So what will happen in this reaction? This oxygen, it has an electron density to donate. So it will attack on this carbon, and on this carbon when it will attack, your halide will leave. So what will be leave? So see here, your Na plus and Br minus will leave. So you will get sodium bromide, that is NaX, sodium halide. And what will be formed? Ether will be formed. So see over here, this CH3O and this group over here. So tertiary butyl methyl ether is being formed over here. So if you have to form a ether in Williamson synthesis, then you have to take your alkoxide ion, then you take your alkoxide ion as tertiary and your alkyl halide as primary alkyl halide. So your alkyl halide should be primary. Okay. So this is Williamson synthesis. So your alkyl halide must be primary 1 degree to get ether. Okay. And if you are going with 2nd degree and 3rd degree alkyl halide, that it will not form an ether. And your reaction will favor elimination over substitution. So over there, it will be follow elimination reaction and not a substitution reaction. Okay, so reason is because the steric repulsion between alkyl group that restricts the SN2 attack. So what happens if your alkyl group will be a 3-degree alkyl group? So the oxygen of your alkoxide, that is sodium alkoxide, when it will attack on 3-degree alkyl halide, then it will be difficult to attack on that 3-degree alkyl halide because of steric repulsion. Because that carbon is a tertiary carbon. It will have 3 CH3 CH3 groups. So that is why in that case, your elimination is preferred over substitution. And alkene is formed in case of 3-degree alkyl halide. If the alkyl halide is 3-degree, then your alkene is the only product. You won't get an ether. Now look at this reaction. In this reaction, see your alkyl halide is a 3-degree alkyl halide. See, this carbon is further connected to 3 carbon atoms. And you have a bromide group that is 3-degree alkyl halide. And this is primary sodium alkoxide which you have. So this is 1 degree. Now what happens in Williamson synthesis, that this oxygen which has its electron density, it attacks on this carbon of your alkyl halide. Now imagine that this carbon is further connected to 3 methyl groups. So it is steric hindrance factor is over here. Okay, so it will be sterically, it is not favored because there is steric repulsion between the alkyl groups. See, these alkyl groups, there is steric repulsion, so your SN2 attack is not favored. Okay, so that is why it is preferred to take primary alkyl halide if you want to get an ether. Okay, so what will happen in this reaction now? This oxygen which has electron density, it will take hydrogen of any of this methyl group and this bromine will leave. Okay, so what will form? An alkene will be formed. See, one of this has lost the hydrogen, so there is carbon double bond CH2. So alkene is formed and Na plus Br minus. So NaBr and this CH3OH. Okay, so CH3 from here and this oxygen and one of this methyl group has lost one hydrogen. So it has formed CH3OH. So CH3OH and sodium bromide, and see here you are getting an alkene, that is 2-methyl propene. This is the longest carbon chain, 1, 2, 3. So when second carbon there is methyl group, so it will be 2-methyl propene. Okay, so if in case you are taking a 3-degree alkyl halide, then this will favor elimination reaction because of the steric repulsion between your alkyl group. So in this case, your ether will not be formed, your alkene will be formed. Okay, so you need to remember this. In Williamson synthesis, it is preferred that if you want to get an ether, then you should prefer 1-degree alkyl halide. Okay, so from 1-degree alkyl halide, when it reacts with the butoxide, which is tertiary butoxide, you get an ether. And when your tertiary alkyl halide reacts with this butoxide, then you get an alkene and not an ether. Okay, so I hope this is clear now. Now, preparation of phenolic ether. Now look in this reaction. In this reaction, your phenol, that is in which the OH group is directly attached to your benzene ring. So your phenol, it is converted to phenoxide ion using a strong base like NaOH. Then this phenoxide ion, what happens? It reacts with your alkyl halide and you get an phenolic ether. Now look at this reaction. Here see phenol and here it is base, that is sodium hydroxide. Now what will happen here? Phenoxide ion will be formed, or you can say sodium phenoxide will be formed, that is Na plus and this O minus. So what is here? Your base gives Na plus and OH minus ions. Okay, so this OH minus will attract this H positive from here. So what will be left? O minus and Na plus. So this is your phenoxide ion, or more specifically sodium phenoxide ion. Now if you have an alkyl halide, that is R, which is connected to any halide, fluorine, chlorine, bromine or iodine, then you will see that this oxygen with its electron density, it will attack on this R group and X will leave from here. So your Na plus and X minus will leave and R group will attach to this oxygen. So this is your phenolic ether. Okay, this is a phenol ring to which your ether is being attached. So this is a phenolic ether. So your phenol is converted to phenoxide ion using a strong base, which is sodium hydroxide. And then this phenoxide ion, it reacts with your alkyl halide. So Na plus and X minus leaves and you get your phenolic ether. Now let us solve one example, that is 7.6. So the question is saying that the following is not an appropriate reaction for the preparation of tertiary butyl ethyl ether. So now they have to prepare tertiary butyl ethyl ether, and it is saying that this is not an appropriate reaction for this preparation. Okay, so what will be the major product of this reaction? And you have to write a suitable reaction for the preparation of tertiary butyl ethyl ether. So see, this reaction is not an appropriate reaction. So it is asking that what will be the major product of this reaction, and you have to write a suitable reaction for preparation of this compound. Okay. So I'll give you 40 seconds to solve this question. You try it and then we are going to discuss it. Okay, so now let's solve this question. Now, can you guess that why this reaction is not an appropriate reaction for a preparation of ether? We discussed this in Williamson synthesis. So what will happen over here, if you look here, then your alkyl halide group is a 3-degree alkyl halide because this carbon is further connected to 3 carbon. So this is a tertiary alkyl halide. So when there is a tertiary alkyl halide, then we prefer elimination over substitution. That means elimination reaction happens here. Okay. And in this case, if you remember, alkene is formed in this case, not an ether. Okay. Because why? Because see here that if this oxygen will attack on this carbon, then if you'll see, then there 3 methyl groups are over here. So in this, it is a sterically repulsion factor comes into the picture. So because there is steric repulsion between the alkyl groups of 3-degree alkyl halide, so it will restrict your SN2 attack. Okay. So in this case, alkene will be formed and no ether is formed. So your alkene will be the major product in this reaction. So if you look at this reaction, here there is 3-degree alkyl halide. Okay, so this is 2-chloro, 2-methyl propane. Okay, if I select this as the longest carbon chain, then 1, 2, 3. On second position, your chloro group is attached and methyl group is attached. And since 3 carbon atoms are there, so the root word is propane. So 2-chloro, 2-methyl propane. And see here, this is your alkoxide ion which is there. Okay, so now what will happen in this reaction? It will proceed by the elimination reaction. So your oxygen has electron density, so it will attack on this carbon, any of this methyl group, and it will take one of its hydrogen. Okay, so take one of the hydrogen, and this double bond will come here, and this alkene, this halide will leave from here. And what will be left? Your ethanol will be left. That is this C2H5O and H from this methyl group. And NaCl will also be formed. That is this Na plus and Cl minus. So you see from this 3-degree alkyl halide, this alkene is formed. That is 2-methylpropene. Okay. So in this case, if you are taking a tertiary alkyl halide, then in that case, an alkene will be formed, not an ether. So that is why if you see in the question, it is a tertiary alkyl halide and an ether is formed. That is why this is a wrong reaction. In the case of ether, your alkene will be formed over here. Now, if we come to the second part, it is asking write a suitable reaction for the preparation of tertiary butyl ethyl ether. So if you have to prepare ether now, then what will be the appropriate reaction for preparing your ether? So if you have to prepare a tertiary butyl ethyl ether, then it will be done by using a primary alkyl halide and a tertiary alkoxide. So alkyl halide should be primary and your alkoxide should be a tertiary alkoxide. So in this case, you have to take a primary alkyl halide. So that is ethyl chloride. Now this ethyl chloride is a primary alkyl halide. And tertiary alkoxide which we are taking is 2-methylpropane 2-olate. Okay, so if you look at this reaction, then it is a primary alkyl halide. Okay, and this is a tertiary alkoxide. So now what will happen in this case? That this oxygen with its electron density will attack on this carbon and your Cl group will leave from here. So this tertiary group will join this oxygen and C2H5 will attach to this oxygen over here. So this will be tertiary butyl ether. Okay, or you can call it as 2-ethoxy 2-methylpropane. Okay, so remember, if you have to form an ether, you will always take your primary alkyl halide. Okay, if you take primary alkyl halide, then you will form an ether in this case. Okay, so let's move forward. Now we'll talk about the boiling point of ethers. Then if we talk about the boiling point of ethers, then the boiling point of ethers is lower than alcohols of comparable molar mass. If you are taking the molecules which have the comparable molar mass, then if I compare your boiling point of alcohols and ethers, then your ethers has a lower boiling point compared to alcohols. This is because in case of ethers, there is no hydrogen bonding, there is only weak dipole interactions is present. So in case of your ethers, there is no hydrogen bonding, there is only the dipole interaction, which is because of your carbon and oxygen bond. So carbon and oxygen bond is a polar bond. So here there is slight polarity in cases of ether. Okay, so it has a net dipole moment. So ethers only have weak dipole interactions. So the boiling points are comparable to alkenes of similar molar mass. So see here, if you have an alkane, that is N-pentane. So this N over here denotes that this is a straight carbon chain with no branching. And this is an ether, which is ethoxyethane. And this is an alcohol, which has 4 carbon atoms. So it is butane-1-ol. 1 because the carbon to which your OH is attached is the first carbon. So it is butane-1-ol. So if you see they have the comparable molar mass. So if you see here in ether and here in alcohol, see the boiling point of ether is 307 and the boiling point of your alcohol is so high, that is 390. Why? Because in your alcohol there is a strong intermolecular hydrogen bonding in cases of alcohol. Okay, so because your alcohol has strong hydrogen bonding and in your ether there is weak dipole interactions. So if the bonding is strong, you have to give more energy for the molecules to get separate. So if you have to give more energy to the molecules, that means the boiling point will be high because the molecules are attached together by strong hydrogen bonding. So you have to give them more energy. So see here, if you are giving more energy, so the boiling point of this alcohol is 390 and of this ether is 307. And they are of comparable molar mass. Okay, so you need to remember that your ethers they have lower boiling point than alcohols. Now, if I talk about solubility of your ethers, then we will see that your ethers, they are miscible in water. Alcohols, they are also miscible in waters because alcohols have this hydroxyl group, OH group, and water also has this OH group. So your alcohols are miscible in water. Similarly, your ethers are also miscible in water of comparable molar mass. Reason is because the oxygen atom which is in ether, it can form hydrogen bonds with water molecules. Now if you look at this picture, then this is your ether, that is ROR, and this is a water molecule, that is HOH. If you see this oxygen over here and this hydrogen of water, if you see this red dotted line, this is representing the hydrogen bonding. So there is hydrogen bonding between oxygen of your ether and hydrogen of your water. Okay, so this oxygen will have a slight negative charge and this hydrogen will have a positive charge. So there is this attraction between this positive and negative charge. So your ether, it has a hydrogen bonding. It forms the hydrogen bonding with water. So that is, it is miscible in water. If you see the solubility of an ether, that is ethoxyethane, it is 7.5 gram per 100 ml water. And if you talk about solubility of butane 1-ol, then it is 9 gram per 100 ml water. So somewhere it is similar. It is differing by only some grams, some per gram, but it is almost similar. Okay, because both of your ethers and your alcohols, they form hydrogen bonding with water molecules. But what happens in case of ether? In ether, they can only accept hydrogen bonds. Okay, because in ethers, this is oxygen. And this oxygen being more electronegative will take this shared pair of electrons from this hydrogen. So this oxygen and ether, they can only accept hydrogen bonds from water. They have nothing to donate. But if I talk about alcohol, in alcohol there is ROH bond. Okay, so oxygen can accept the electron density from hydrogen of your alcohol, and the hydrogen of your alcohol can donate your electron density to oxygen of your water molecule. So in alcohol, it is both ways, that it can accept also and it can donate also. So it forms better hydrogen bonding in case of your alcohol as compared to ether. Okay, so that is why of alcohol it is little bit more, that is 9 gram per 100 ml. Okay, and if you see in this ethoxyethane and this alcohol, then both have the same non-polar part. Okay, it is differing little bit because of their different bondings with water molecule. Okay, so here if I talk overall, then your ethers, they are miscible in water. Now let us solve this one NCERT question, that is 7.25. The question is saying that illustrate with examples the limitations of Williamson synthesis for the preparation of certain types of ethers. So you have to tell the limitations of your Williamson synthesis for preparation of certain type of ethers. So I'll give you 30 seconds to solve and then we will discuss. Okay, let's discuss the solution. Then if we talk about the limitations of Williamson synthesis, then Williamson synthesis proceeds through SN2 mechanism. So when it proceeds through SN2 mechanism, so we take primary alkyl halide, and in that case your ether is formed. So your alkoxide ion, they attacks your primary alkyl halides, that is your RO minus Na plus, that is your alkoxide ions, they attack your primary alkyl halide. So see here, this is a tertiary alkoxide and this is a primary alkyl halide. So what will happen? This oxygen has electron density, so it will attack on this carbon and your halide group will be left. Okay, so it will form sodium bromide and an ether will be formed. So if we continue the solution, we will see that what are the limitations that secondary or tertiary alkyl halides, they favor elimination over substitution. We discussed that whenever we are taking an example of secondary or tertiary alkyl halide, they will always follow elimination. They will favor elimination over your substitution because of the steric repulsion factor. It will be difficult for the oxygen of your alkoxide to attack on tertiary or secondary alkyl halide, because in tertiary there will be 3 methyl groups and in secondary there will be 2 methyl groups. So steric repulsion factor will come into the picture. So it will be difficult to attack. So it restricts your SN2 attack and it favors the elimination attack. So alkoxide ions, they can act as strong bases, facilitating your elimination reaction. So when your elimination reaction is happening, then your alkoxide ions, they act as a base in that reaction. So what base do? Base accepts proton. That is, it accepts H plus ions. Okay. So in case of 3-degree alkyl halide, alkene is the only product. So if this is a 3-degree alkyl halide, so in this elimination will be favored and alkene will be formed over here. Okay. So that is this NaOH, which acts as a base over here, will abstract one of the H from this methyl group, and this bond will come down and this bromine will leave. So that is, it will form a carbon-carbon double bond. Okay. So you will see an alkene will be formed and you will get CH3OH. That is CH3 from air here, O and H from any of this methyl group. So you will get an alkene in this case. So this was the limitation. Now if we summarize whatever we studied in today's lecture, so we saw the preparation methods of ethers. So first we discussed about ethers. How does ethers look like? So in ethers, the hydrogen of your hydrocarbon, it is replaced by an alkoxy or an aryl oxy group. Okay. And we discussed there are 2 types of ethers, symmetrical and unsymmetrical. In symmetrical ethers, the 2 groups that are attached to the oxygen is same, and in unsymmetrical ethers, the 2 groups that are attached to the oxygen, they are different groups. So we then discussed the preparation methods. First method we discussed dehydration of alcohols. In dehydration of alcohols, I told you it is not always necessary that if you are taking an alcohol and reacting it with a protic acid, then it is not necessary an ether will be formed. It depends upon your reaction conditions. If reaction temperature is 413 Kelvin, then ethers will be formed from alcohol and it will favor the substitution reaction. But if the temperature is high, that is 443 Kelvin, then from your alcohols, your alkenes will be formed. And this will favor your elimination reaction, not the substitution reaction. Then I discussed about Williamson synthesis. In Williamson synthesis, it works best with primary alkyl halide. So for your sodium alkoxide to attack, it should be a primary alkyl halide, because if it is a primary alkyl halide, there is no steric factor over there. So in this case, your substitution favors. Okay. And you get from an alkyl halide, you get an ether. But when you talk about secondary and tertiary halides, then it favors elimination and it gives alkenes because of the steric repulsion factor in that case. Okay. So it favors elimination and you get an alkene. Then we discussed about some physical properties of ether. So we see that ethers, they have a lower boiling point than comparable molar mass of alcohols. Okay. Why? Because in alcohols there is strong hydrogen bonding, and in ethers there is weak dipole-dipole interactions. So if there is strong hydrogen bonding, you have to give more energy for it to get separate. So that is why your ethers have lower boiling point as compared to alcohols of comparable molar mass. So there is no hydrogen bonding between the ether molecules because ether is in the form alkoxyalkane. Okay, so there will be no hydrogen bonding between the ether molecules. But if I talk about with water, then ether is soluble in water because it can form hydrogen bonding with water molecules because your ether has the oxygen group and that oxygen group can interact with your hydrogen of water molecule. Okay, so it will attract the electron density from that hydrogen. So oxygen will have a slight negative charge and hydrogen will have a slight positive charge. So there will be attraction between the oxygen of your ether and hydrogen of a water molecule. So that is why it is soluble. But when we talk about alcohols, then in case of alcohols, there is both ways because there is OH bond in alcohols. So it can accept also and donate also. Okay, so that is why for alcohols it is little bit more as compared to ether, the solubility. But both are soluble in water. So this is today we discussed about the reactions of ethers. So I hope today's lecture is clear to you. Thank you students for attending this lecture.